Hello and welcome to Lecture 6, where we're going to cover sections 3.1 to 3.2 from Survey 11th edition. The topics covered in these sections in the third chapter are 2D motion with constant acceleration. Most of the time that's going to mean projectiles. All right, so I'll let you read the objectives for yourself. Let's just get into the key terms. There's not too many of them, but I want to define them. So first of all, we have 2D motion with constant acceleration. The term kind of gives away the definition, but what it is it's constant acceleration vector that creates non-constant velocity vector. All right. So the key idea here is that these are both vectors. They're going to have both x and y components. In other words, I hat and j hat components. Acceleration is usually along one axis, so it only affects one component of velocity. All right. Now, I have one example where that's not the case, but that's definitely the unusual case. What is a projectile? Well, any object whose only acceleration is gravity. If that sounds a lot like free fall, it should. Projectiles are in free fall. The only difference from what we talked about before in the section or the sections that covered free fall is that projectiles usually also have constant velocity horizontal motion. All right. Now I say usually because really, I guess you could have a projectile that goes straight up and straight down. And so in that sense, free fall is a case of projectile motion. But most of the time, a projectile is an arcing object, arcing through the air. It has a very characteristic type of trajectory. A trajectory is just a term for the position of an object instantaneously mapped through space. Something like this, all right? So essentially, it's just the x and y position of an object. All right? So for example, you could say that each of these is a point along the trajectory of a projectile being an object that is under the acceleration of gravity alone. Okay? So what's the deal with a projectile? Well, we can imagine something being launched with an initial velocity v naught. Okay? That is a v naught vector. That initial launch vector has two components. It has a vertical component and a horizontal component. It has an angle, in this case measured relative to the horizontal. All right? There is also gravity acting on the projectile. That is the only acceleration in the system. Notice that gravity points directly down. Based on the coordinate system that I've chosen, which is by far the standard coordinate system, g would point in the negative y direction. After some time, the projectile moves up. Its velocity vector has become shorter and has become more horizontal. At the very top of the arcing projectile trajectory, the velocity is entirely horizontal. So we can see then that Vy at maximum height is equal to V naught x. Okay? So in other words, the total velocity vector is equal to the initial horizontal component of velocity. All right? And this is Vy max. And notice here that this is not meant to say the vertical component. So this is not the vertical component. Instead, this is just the total velocity vector at y max. The notation was more confusing than I intended. But this would be referring to the entire velocity vector, not a particular component. All I'm saying is that at this point, the entire velocity vector, the hypotenuse, well, is just one leg of the initial. Because what's happened to v naught y? It's gone away. V naught y is momentarily zero at the top of the projectile trajectory. Why is that? Well, the same reason that velocity or speed is momentarily zero for something that's thrown straight up. It's got to be at rest at that moment where it's turning around. All right? On the way back down, the projectile picks up speed until finally, when it reaches the ground, it has a vector which has the exact same magnitude and direction of x initial component, but has a vertical component that is equal in magnitude but opposite in direction, assuming that it landed on level ground. In that case, we may refer to the range as the total distance it covers along that level ground. Okay? So let's take a look at the key formulas. So a lot of this will be either familiar from our kinematic equation notes or from our notes where we introduced vectors. So it's not new stuff, it's just new the way that we're combining it. All right? So what are our equations? So initially we have the equations for initial velocity. All right? Why initial velocity? Well, because often that's an important part of the problem. We know something about the initial velocity or we seek to know something about the initial velocity. Now, any velocity could be found or could be important in a problem. It's just that usually the initial one is the one you care about. hence its inclusion in the key formulas. So the idea is that the initial velocity vector is composed of two components, themselves vectors. We can express the magnitude of either one of those component vectors as v naught cosine theta naught or v naught sine theta naught, respectively, again assuming that theta naught is measured relative to the x-axis, the horizontal. If it's not, well, then that cosine and sine would have to change in some way, okay? But most of the time it is. All right? All right, well, moving right on, we have the position and velocity in the x direction, okay? Well, what's going on with these equations? Well, here's our position equation, all right, and here's our velocity equation. They're actually quite simple. That's because there's no acceleration. Acceleration in the x direction is 0. There is no acceleration. Thus, there is no third term with 1/2 axt squared because ax is 0. Likewise, there's no term here of axt because, again, the horizontal acceleration is 0. Okay? So these two equations for projectile motion in the x direction simplify dramatically, so dramatically that we see that the velocity in the x direction is unchanging. Of course it's unchanging, though, if you stop and think about it, because there's no acceleration in that direction, so there's nothing to change the horizontal component of the speed of the projectile, right? Okay, well, in the y direction, there's a bit more going on, and in fact, the equations are identical to what we'd see for freefall. These are absolutely verbatim the equations for freefall, because really what happens in the y direction and what happens in the x direction are independent of one another. So in the y direction, it might as well be freefall. It is from a certain perspective if you are moving along with the object, and in the x direction, it's just something coasting along at constant speed. All right. Together, though, this set of 5 equations represents the equations of projectile motion. All right? A really common type of problem that we want to be able to become familiar with, hence the focus on this particular set of equations. All right? All right, we got one more that I want to show you. This one right here is just derived from the previous 5. And all it is an equation where we've eliminated time from the equation, and instead we've solved for the vertical position as a function of horizontal position. The equation looks a little unwieldy, but what's actually nice about it is it's the equation of a parabola. So it's telling us that the vertical position indeed has a parabolic dependence on the horizontal position. That's actually quite interesting. It tells us that the vertical position has a parabolic dependence on time and on horizontal position. Pretty neat, all right? And it would also allow us to solve for the instantaneous vertical position if we knew the instantaneous horizontal position, or vice versa. Okay? All right, so I have 4 types of problems that I've identified in my chosen examples. Type 1 problems are ones that involve projectiles that are launched from and land on level ground. That's the simplest case, like the projectile trajectory that I showed in the example key terms. Type 2 are fairly complex problems that involve projectiles that are launched from a higher or lower point than the point at which they land. Okay? Finally, we have type 3, fairly complex problems that involve projectiles ending their trajectory by crashing into a wall or other vertical obstruction. So I set that type apart because it's important to really think about that, because most of the time we take for granted that what's going to stop the path through the air is it crashing into the ground, whether the ground is above or below where you started. Like shooting something off a cliff, it's still the ground that you're crashing into. But what if you crash into a wall or a pirate mast, like an example I have? Well, in that case, the actual equation setup, the equations we focus on, are a bit different. They still come from those same 5. However, we might draw our attention more to some rather than others. And finally, the 4th type of problem is the complex type, and these are ones that involve non-projectiles, like rockets, that experience a second constant acceleration. So the acceleration is still constant, so it's still kinematic equations, but it's actually straight up not a projectile anymore. We only have one type of example like that, and it's the only type of example in this practice set that doesn't really use the 5 equations that I just boxed off on the previous page. Instead, it really just comes from going back to the fundamentals of the kinematic equations in x and y, okay? All right, so let's take a look at our first simple example. A long jumper is running at a speed of 9.39 meters per second when she launches herself off the ground at an angle of 14.5 degrees with the ground. The ground is perfectly level. How much time will she spend in the air? Okay, well, let's see. So first of all, I'm going to want to use a position function for y, and I want to find the time by acknowledging that y equals y naught, because she's going to start at, say, y equals 0, and she's going to end at y naught equals 0. All right? Or rather, she's going to end at y equals 0, and she's going to start at y naught equals 0. Now, I could have called them 5 and 5, or I could have called it 100 meters above sea level. It wouldn't matter, because the fact is they're equal to each other. Thus, they're going to cancel out in the equation that we have here, which is one of the kinematic equations, in fact, kinematic equation number 2, but specialized for free fall because it has a negative 1/2 g rather than a plus 1/2 a. All right, but anyway, moving on. Let's go ahead and solve that. When we solve this up, I'm just going to set up the quadratic equation, but the quadratic equation sure simplifies a lot here because our c term is 0. Thus, the minus 4ac part of the quadratic equation, which would be inside the root, right, part of the radicand, is just 0. So, oh, that's nice. That means that this is just going to clear up to have two solutions. One is going to be 0. Why would 0 be a solution? Well, because if this is negative, and I take the square root of v naught squared, then I'll just have v naught squared, if it's positive, then I'll just have v naught squared plus v naught squared. Well, negative v naught squared plus v naught squared. Well, then they would just, let me say that one more time, Negative v naught y plus positive v naught y, because that would be taking the square root of the square. Okay, they cancel out. Well, then the whole numerator just becomes 0. All right. On the other hand, if I take the minus case, well, then I'd have negative v naught y minus v naught y, in which case the numerator becomes negative 2 v naught y, and then the negative in the numerator cancels with the negative in the denominator, and then we're left with just v naught y over g. All right. And another thing to notice is actually I do have a small typo here. This should actually just be g, because down here this is in the quadratic formula. Of course, it is t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. But here our a is 1/2 g, so the 1/2 should have canceled with the 2. So that actually, it should just be g. And you can see I have it correctly here. So please excuse that superfluous 2. Okay? All right, so then this is the time in the air, 2 v naught y over g. All right, that's the total time in the air for any projectile that's launched on level ground. So this is actually a pretty useful equation as long as you're on level ground. The total time spent in the air. If we plug in our particular values, we end up, as you can see, right, I just plug in 9.39, which is the magnitude of the initial velocity. Since I'm only interested in the vertical component, I take sine of 14.5, sine because the initial velocity is something like this. We have the initial x component and the initial y component. Here's theta. Well, sine is opposite over adjacent. Opposite was the vertical side, hence sine. SOHCAHTOA, right? And then I just divide by g, 9.8, and that gives me 0.48 seconds. That's how long she spends in the air. All right, let's find out how far she jumps. Well, the great thing about having part A first is it's going to be helpful in us solving part B, because I'm going to take the time from part A and just plug it into my horizontal position function. Notice again, no acceleration. And so I simply plug it in. What I've done here, as you can see, is I've gone ahead and wrote v naught x as v naught cosine theta in the same way that I wrote v naught y as v naught sine theta. And then I've replaced t with the whole expression that I solved above. I did that because then I can come up with an equation which is often called the range equation. But again, be careful, because the range equation and that title makes it sound like it's some universal equation, but it only applies to level ground like the long jumper. But we can plug in our values for this particular problem, right? It's got a cosine and a sine, so it depends on what's happening in the horizontal and the vertical. And that makes sense, okay? And then we end up with 4.36 meters. By the way, if you think about this formula, the angle that will always give maximum range for a particular magnitude v naught is 45 degrees. All right, give it a try, plug in values, or think about it mathematically. Finally, what is the maximum height that she reaches? All right, well, there's a couple ways to go about this. We could use v equals v naught y minus gt to find the time to reach y max, and then use the position function in y to actually find it. Or we could just use symmetry of the jump to find the time to max height as half the total time in the air, because it has to be. She has to spend just as much time going up as coming down. So in that case, it's just 0.48 divided by 2, which gives us 0.24 seconds. All right? Now finally, a little bit trickier question. What is the height of the jumper when her velocity vector makes an angle of 5 degrees with the horizontal. Now remember, initially her initial velocity vector makes an angle of 14.5 degrees with the horizontal. And at the very top of the arcing jump, we know that her velocity vector makes an angle of 0 degrees with the horizontal because at that moment, for an instant, she's traveling entirely horizontal before she starts on her way down. And we know that that would take 0.24 seconds to get to that point where she's at maximum height and is instantaneously traveling horizontally. But what about where she's somewhere in between? What if I tell you the angle and ask you, I could ask you for how long, the time, and you know it would be something less than 0.24, but instead I'm asking you for the height, right? Let's see what we get. So we know that Vx equals V naught x. In other words, we know that the horizontal velocity is unchanging. We also know that tangent theta is Vy over Vx. Notice this is not tangent theta naught equals V naught or Vy naught over Vx naught. Instead, this is for any instantaneous point in the jump. All right. We also know that Vy is equal to V naught x, because again, I've just replaced Vx with V naught x, times tangent theta. All I've done here is just isolate V naught y or solve for it at any point. Okay. So then I'm going to go ahead and find Vy when theta equals 5 degrees. And notice here I have V naught of cosine theta naught times tangent of theta. So both the 14.5 degrees and the 5 degrees show up in my calculation. And I end up with a Vy of 0.795. Okay? And that definitely is larger than V naught y. Check it for yourself. Excuse me, smaller than V naught y. Check it for yourself. Because it has to be, because of course she has slowing down in the y direction. All right, and now I'm simply going to use the kinematic equation that we haven't used yet. Vy squared equals V naught y squared minus 2g times delta y. Delta y is what I want to solve for. I go ahead and solve for delta y. I'm going to distribute that negative to reorder the terms in the numerator, as you see here. And then I just plug everything in. All right, I plug in V naught y, shown right here. I plug in the instantaneous Vy, and then I just divide by 2g. And again, the change in order here is due to distributing the negative. Okay? And I end up with 0.250 meters. And by the way, the maximum height she reaches, I think, is 0.253. So it's actually pretty close to, maybe it's 0.28. I think it's at 0.28 meters. So she's actually pretty close to the maximum height she's going to reach. Because that's the thing about the angles. It falls off quickly at the end. And it kind of, but it's not linear, in other words. The angle is not changing at a linear rate. All right? So first example done. That's the simple one. Let's look at some more complex ones. I'll go through these at a kind of a faster pace so we can kind of see them, and then you can refer back to them later. Okay? So we have a couple where we're dropping something from a higher height than it is landing at. All right? So in the first one, it's a package being dropped. So an Alaskan plane drops a package of emergency rations to stranded hikers as shown. The plane is traveling at a horizontal velocity of 40 meters per second at a height of 100 meters above the ground. Where does the package strike the ground relative to the point at which it was released? And what are the horizontal and vertical components of the velocity of the package just before it hits the ground? All right, so here in the picture, I've just pointed out that r is one of the things that I'm interested in. And here I'm showing that the initial velocity vector as well as the growing velocity vector as it accelerates downwards. All right, so we're going to find the total time in the air by looking at the vertical position. All right, so I'm just going to put in what I know in terms of my known variables and then solve for TF. TF here you think of as time of flight or time in the air, and it's 4.52 seconds. Total amount of time it spends before it hits the ground. Well, then I can just take that time, right, kind of similar to that we did in the previous problem. All right, I'm just going to take that time and then find out how far it went. So I'll just plug that into V naught x times the time, because it has to be traveling in the x direction the whole time that it's in the air, and it's traveling at a constant rate in the x direction for those 4.52 seconds. So that tells me that my horizontal range is 181 meters. All right, pretty cool, right? And then I can go ahead and say, well, okay, well, the x component of final velocity is unchanging compared to the initial component of initial horizontal component of velocity. It's just 40 meters per second, as stipulated in the problem. But what about the vertical component of velocity? Well, that one's going to be speeding up. All right, and it ends up being 44.3, so actually kind of similar, right? So then what's the angle going to be? Well, we're not actually asked for the angle, we're just asked for the two components. If we did want to find the angle at which it crashes in the ground, we could just use inverse tangent to do so, and it's going to be something pretty close to 45 degrees because the two components are pretty close to being equal in magnitude. All right? Make sense? So in this problem, we dropped something. When you drop something from a plane, it has an initial vertical velocity of 0 because it was dropped, and it has an initial horizontal velocity equal to that of the plane. All right? Good things to kind of make sure that you're clear on. Now in this case, we're not dropping something from a plane. Instead, we're throwing something from a window, and unlike the plane, the initial velocity is not entirely horizontal. So arguably example 3 here is a little bit more complex because the initial velocity has both a vertical and horizontal component, because our little girl is throwing a ball 20 degrees below the horizontal, but we're asked for the same sort of thing that we're asked for in example 2, in other words, the range. Okay? So let's take a look at that. So first of all, I'm going to find v naught y by simply taking v naught times sine of theta. All right? In this case, theta is negative 20 degrees, which gives me a negative value of v naught y, which makes sense because it should be in the negative y direction. It should be pointing down. Now, is that consistent with our coordinate system? Absolutely, because 0 is up and negative 8 is down below. Okay? So then we have to find the time in the air. So to find the time in the air, we're going to take that information, that initial vertical velocity, and then we're just going to plug it into our displacement in the vertical direction. All right? And then we just need to solve for t. So here I say using the quadratic formula or just using a calculator, like graphing it or using a polynomial solver in a calculator, I find that t is 0.998 seconds, the total time that the balloon spends in the air. And then, like above, I'm just going to find the range. Let me zoom in a bit. By multiplying the unchanging horizontal component of the initial velocity times the total time spent in the air. So that's 10 meters per second times cosine of 20 degrees, because after all, I just want the horizontal component, times the time spent in the air. Now, cosine of a negative angle is the same as cosine of a positive angle, so that's why I get a positive value, or 9.18 meters. All right? All right, so let's go on to a concept question. 3 projectiles are shot from the edge of a cliff. Number 1 with an initial horizontal velocity of 0, number 2 with a small initial horizontal velocity, and finally number 3 with a large initial horizontal velocity. All 3 have an initial vertical velocity of 0. Which projectile hits the ground first? Well, maybe you can guess. They all hit at the same time, because the time spent in the air is independent of the initial vertical velocity and, of the initial horizontal velocity. And since that's the only thing that varied between the 3 projectiles, well, they all have to hit at the same time. But which projectile hits the ground with the least speed? Well, that would be number 1, because the final velocity is found with the Pythagorean theorem of the 2 components of final velocity. And notice that the final velocity in the x direction is the same as the initial velocity because it's unchanging, because there's no acceleration in the x direction. So anyway, and since v naught x is the least for 1 and v final y is the same for all 3, well, then you can say then that v final has to be the smallest for number 1. All right? All right, so now let's do another non-level ground problem, but in this case, it's going to be one where we're going up rather than down. All right, so unlike example 2 and example 3, where we're launching something from a higher point, now we're launching something from a lower point. A cannon launches a ball as shown in the figure. The ball lands exactly at the edge of the 135-meter tall cliff as shown, a horizontal distance of 195 meters from the cannon. The ball spends 7.6 seconds in the air. Then what is the initial velocity and angle of launch of the ball? All right, and obviously ignore drag. All right, so we're going to use 2 equations here. So I'm labeling one with a purple dot, and that's my horizontal displacement, and then my vertical displacement. Okay, labeled with a green dot. We know the following information. We know y and y naught. We know x and x naught, and we know t. All right. So that's interesting. That's actually a lot of information. We haven't seen a problem where we're given the total time it spends in the air. Okay. So then what are we actually looking for? Well, we're just looking for the initial velocity and angle of launch. So actually, we're just trying to find v naught x and v naught y. All right. So let's go ahead and set up the purple equation, plugging in what we know. So there's our single unknown v naught x in that equation. And then we do the same thing with our green equation, our vertical displacement, and the same thing. We end up with a single unknown v naught y. Okay, well that means we can just solve each one individually. So v naught x then just becomes 25.7 meters per second, and v naught y just becomes 55 meters per second. Okay, and well, with that information, we can then say that the overall magnitude of the initial velocity is 61, and the angle using inverse tangent, all right, and that's the angle as shown in the figure, measured relative to the horizontal, is 65 degrees. Oh, pretty cool. Now, In this problem, I cheated a little by labeling it as blue because there actually is a bit of a horizontal restriction on the problem as well, because it kind of is crashing into a wall because it's landing at an exact point that is specified both in x and y. All right, so, but let's look at the next one where there's definitely a clear condition of something crashing into the wall as all our other projectiles have crashed into the ground. A cannonball is launched from a pirate ship at an initial velocity of 45.8 meters per second at an angle of 25.1 degrees above the horizontal. How fast is the cannonball traveling when it smashes into the mast of a merchant ship at a horizontal distance of 65 meters? And at what angle does the cannonball hit the mast? All right, so notice here that I'm given the horizontal distance to the mast. That's in contrast to many of the other problems where we're given some sort of vertical distance to set up the problem. And the mast, we're assuming that it's entirely vertical. It's stopping the projectile. So the setup would look something like this. We have some initial velocity. The projectile is arcing through the air, taking that parabolic path, but then it's not able to complete it because it hits our wall, in other words, our mast. All right? Okay, so start with the equation for horizontal displacement. X equals x naught plus v naught x times tf being time of flight or time in the air. All right, and then I just go ahead and solve for the time that it spends in the air, which is 1.57 seconds. Okay, this is similar to other problems, but actually easier because before, if it was vertical and I had to solve for the time in the air, I always had to use the quadratic formula. But here, since there is no tf squared, I can solve for it more directly and get 1.57 seconds. All right, so then I'm just going to use the following two equations. All right, and I get for the x component of velocity, it's just going to be 41.5 because it doesn't change. All right, but then for this one, I'm going to have to actually solve it, and that's for the vertical component of final velocity, and it ends up being 4.07 because it's been slowing down quite a bit. So it started with a pretty large vertical component of velocity, but of course gravity in the vertical direction has been slowing it down over the 1.57 seconds it's spent in the air. So then the final vertical velocity when it crashes into the mast right there is only 4.07 seconds, meters per second. All right, so then we'll find the overall speed of the cannonball when it crashes into the mast using the Pythagorean theorem, and it's 41.7, okay? And as far as the angle, it ends up being 5.6 degrees. So we're nearly at the top of the trajectory, so the angle is quite small relative to the horizontal. But that's probably what you'd want when you hit a mast, because you want to really deliver a lot of force to it, not just try to pull it upwards. All right? Okay, so hopefully that makes sense as a variation on a projectile motion problem. Okay, so question 2, another concept question. An elevator is moving upward at constant velocity with constant acceleration. The dashed curve shows the vertical position of the ceiling of the elevator as a function of time. At the instant indicated by the dot, a bolt breaks loose and drops from the ceiling. Which curve best represents the position of the bolt as a function of time? All right. So in a sense, this is not quite a projectile problem because the elevator is accelerating with an acceleration other than gravity. But once the bolt breaks loose from the ceiling, then the bolt is in fact a projectile. All right. So which must be the path? Which of these 5 options, A, B, C, D, or E, could be the only correct answer? All right. I want you to have a guess, but I'm going to tell you now. It's B. Why is it B? Well, for 2 reasons. Because at the moment of release, the velocity, delta y over delta t, is by definition tangent to the curve. So that means that actually the only 2 options that are even valid based on the very definition of velocity are A and B. But we can eliminate A because A doesn't arc downwards. And of course, once the bolt becomes a projectile, its velocity and its position as a function of time has to take a parabolic path. All right? Its velocity would take a linear path. But we're not, but the graph doesn't show velocity, it shows position. All right, so hopefully that makes sense. Great question. All right, so now I have some another example. This is a big one, and I'm just going to kind of quickly summarize it so we can wrap up this this lecture. The idea here is it's really a combination of 2 types of problems. In the first one, this would be a problem that's entirely defined by vertical displacement. We're just finding how basically it's very much like the Alaskan supply drop. But then in the second version, in part B, we're actually told that we want specifically to have the box travel horizontal distance of 400 meters. So it's kind of like shooting the projectile up and having it land on the edge of the cliff. But the thing we're going to control for is the initial velocity, again, like that problem. But now we have the question, well, do we want to angle it downwards or angle it upwards? And we'll find that the only way to solve the problem is to angle it upwards. All right? So I'm just going to kind of go through and show. In part A, we find time of flight by looking at vertical displacement, find the value, plug it into the x displacement, and that gives us our range, 290 meters. So we solved for x, that was our unknown. In part B, however, we have to solve for v naught. So then now we start with x final, just like we would with the pirate ship. So we start with the horizontal displacement, find the time of flight based on that 400 meters, and then use that time in the y motion equation to get a y final that we know has to be 200 meters, or rather just set up a position function in the y direction, and then solve for v naught y. When we solve for v naught y, we do it at 21 meters per second. That tells us that we have to angle the package up when we release it if we want it to travel 400 meters, having released it from a height of 200. All right, so it's upward, and we know because of the sign, since we stuck with our coordinate system of positive y being up. Okay? Now that one last problem, a problem that isn't a projectile motion problem, but still is a constant acceleration problem. A hot air balloon is rising at a constant velocity of 11 meters per second when a child launches a toy rocket off the side of the balloon's basket. The rocket has a constant thrust acceleration of 2.04 meters per second squared. The child launches the rocket at an angle of 20 degrees above the horizontal, and the balloon is at an altitude of 755 meters above the ground. Then what will be the altitude of the balloon when the rocket hits the ground? So how do we do this? Well, here's our picture. So the key idea is that the motion in x direction, although it could be useful for a variation of the problem, isn't actually needed here. We only care about the motion in the y direction because the constraint on the system is the rocket eventually hitting the ground. Notice, however, that our acceleration isn't just g anymore. It's ay minus g. Why is that? Because the acceleration of the rocket is combining with the acceleration of gravity. But then we set it up just like we would before. We use the quadratic formula to solve for the time that it spends in the air. It ends up being 14.1 seconds, a greater time than if there had just been gravity, because the upward acceleration of the rocket effectively makes it fall slower, all right? And then we just simply use that value to find out, and by the way, I rejected the solution from the quadratic formula because it was negative, it had no physical meaning. Negative time doesn't make sense. So then we just take that 14.1 seconds, multiply it by the constant upward velocity of the balloon and the initial altitude of the balloon, right? To get, because it started at 755, to find out that the balloon finishes at 911 meters above the ground by the time the toy rocket hits the ground. The toy rocket that is not a projectile because it has its own additional acceleration. And I know I moved through that at a good clip, but I do want to wrap this lecture up. So please refer back to this if you need to look at it more carefully. All right, well, thank you so much for listening to this lecture. It was a big introduction to dealing with projectile motion, which I know is kind of a big turning point in the class of really bringing a lot of ideas together that we've seen previously. Please ask me any questions. I'll see you in office hours and all of that. All right, thank you so much. Bye.